All right, so now we're going to take a look at and we're looking at organic compounds that have collections of atoms that are other than C's and H's, or maybe even different types of bonds. And when we see that, we can identify what are known as functional groups. And what functional groups are just collections of atoms or types of bonds that give an organic molecule a particular characteristic or several characteristics, and they also dictate the types of reactions that that organic compound is going to undergo. So in lots of cases, identifying the functional group that's present in an organic compound, it helps you to determine the types of reactions that it can undergo. So this first one here is written out for you or shown. So in this case, this is known as an aldehyde because it actually contains the C double bond O connected to an H, right? And sometimes this is just abbreviated as CHO, or in this case, you have the C double bond O connected to the H. So we'll take a look at a couple other ones. And usually what we're going to look for are atoms other than C's and H's, like I mentioned previously. So if we take a look at the second one, we'll see that there's an O connected to a C. So that's this structure here. We have a CH3 at the bottom. We have a C and a double bond CH2 at the top, and then an H over on this side. So what may automatically draw your attention, again, you want to look at atoms other than C's and H's, would be this, right? So you have your oxygen, and we see that it's connected to a carbon. So we have that C double bond O. That itself is known as a carbonyl. But when that carbonyl is between other things, or if it itself is connected to other specific things, it belongs to a particular functional group. So in this case, the carbonyl is between a carbon on one side and a carbon on the other side, right? So that entire thing, carbonyl between two carbons, is known as a ketone. Okay, and a ketone, C double bond O between two carbons, and then whatever else is connected here, it doesn't really matter. This is what we're looking for, right? That tells us that we're dealing with a ketone. So that's going to be this functional group that's present. If you look at the other one down here underneath, we have that OH. That OH is connected directly to a carbon. That OH is a hydroxyl group, and that identifies this family as an alcohol. All right, so you want to go through that list of organic functional groups, get familiar with it, and how to identify the different functional groups. All right, so here we're taking a look at naming some of the organic compounds that have halogens in them. And we're going to call these alkyl halides generally, or sometimes they're called haloalkanes, depending on what else we have in the molecule. So haloalkanes would have halogens as part of the alkane itself. So when you have these halogens present, so things like fluorine, chlorine, bromine, etc., when you incorporate them into the name, the actual name changes. So fluorine becomes fluoro, chlorine becomes chloro, and so on and so forth. So the same thing is going to apply here. We want to establish our longest continuous carbon chain to begin with. So if I look at the one down here at the bottom, so I have a skeletal chain going all the way across, like this. Here I have a BR and one stick, I guess, if you want to call it that. And then another branch coming off here. So first thing we want to do, we want to identify the longest continuous carbon chain. And we can see in this case that it's right across the middle. Okay, and we have a total of, let's see, 1, 2, 3, 4, 5, 6, 7. So that would be hept. They're all carbon-carbon single bonds in this thing. So this would be heptane. And now we have a choice. Well, before we have a choice, let's see what else is present. We have this branch or this group. This is a 2-carbon branch that's called ethyl as our group. we have a 1 carbon branch here. That's a methyl. And then we have a Br, and now we know that's called bromo. So we want to number the chain, the 7 carbon chain, appropriately to give the lowest number possible for these substituent groups. So obviously I'm going to start numbering from the right side. So that's 1, this will be 2, 3, 4, 5, 6, and then 7. So now this methyl up here would be called a 2-methyl. This bromo needs to be called a 2-bromo, and then the ethyl will be a 3-ethyl. Then we incorporate all of these substituent groups alphabetically. So B comes earlier in the alphabet, so 2-bromo. B, C, D, E. Ethyl comes after, 3-ethyl. And then the methyl comes last. Well, I guess third in the substituents. Then 2-methyl. And we add in the heptane at the end. All right, so this all starts with identifying the longest continuous carbon chain first, then numbering it to give the lowest number possible to the substituent groups. All right, so now we're going to take a look at identifying and drawing primary, secondary, and tertiary alcohols. And again, when you're drawing things, I suggest that you draw it on the sheet of paper first, then transfer it over to ALEKS. So it says draw the skeletal line angle structure of a secondary alcohol with 6 carbon atoms, 1 oxygen atom, and no double or triple bonds. All right, so the key thing here is that it's a secondary alcohol. So secondary alcohol, we abbreviate as this. So as with all alcohols, they're going to contain the hydroxyl or the OH groups. Secondary alcohol means that the hydroxyl is connected to a carbon. And this carbon itself needs to be connected directly to 2 other carbons. So we can start with that first, right? So I have my OH connected to a carbon, and then that carbon needs to be directly connected to 2 other carbons. And then we'll just identify or fill in the remaining parts of the description, right? So this here, this identifies this as a secondary alcohol. I can then go ahead, fill in this hydrogen, this carbon, I'm sorry, needs to be connected to 1 other H. And then I can just make up the remaining carbons, right? So I can have a CH3 on one side. So 1, 2, 3, 4, 5, and then 6. All right, so I have my 6 carbons, 1, 2, 3, 4, 5, 6. My H's are there, and then my oxygen here as part of the alcohol. There aren't any double or triple bonds. So if I need the skeletal structure for this, I have 1, 2, 3, 4, 5, 6 across the middle, 5, 6, and then my OH right there. All right, so when I draw my skeletal structure, so 1, 2, 3, 4, 5, 6, and I have my OH coming off of the second one. And there's actually multiple secondary alcohols you can draw for this. This is just one option. So I have my OH attached, and if I check that, that should be correct. All right, so secondary versus primary versus tertiary alcohols, we need to know the difference between those, how to interpret them, but then also how to draw them. All right, so now we're going to take a look at naming and drawing our alcohols. So, naming our alcohols if we are provided with the structures. So here I have, let's see, 1, 2, 3, 4, 5. We have an alcohol like this. We know it's an alcohol because it has the hydroxyl group. So same thing here, we want to establish the longest continuous carbon chain. So in this case, the carbon chain starts here. So that's 1, 2, 3, 4, 5. So this would be a pentane thing because it's all carbon-carbon single bonds. Where is the OH attached? So we want to number it to give the lowest number possible to where that OH is attached. So this has to be carbon 1, 2, 3, 4, and 5. This is an alcohol. Okay, which means that we're going to drop the ending we're going to replace it with OL. So this becomes pentanol. So the OL tells us that we have that OH group present, and the OH is attached to carbon number 1. So we need to say 1-pentanol. And that would be, in this case, a primary alcohol. If we take a look at, let's do the second one. So we have 1, 2, 3. We have an OH over here, and we have an OH over there. All right, so again, in this case, our carbon's longest carbon chain across the middle. Okay, so that's where the carbon chain starts and ends. Obviously, we have our OHs, one here and one there. We want to number the chain to give the lowest number possible to where those hydroxyl groups are attached. So we want to start numbering on the right side. That's carbon 1, 2, 3, 4, and 5. Okay, so again, now this is going to be our pentane. We have 2 OHs. So normally, if we had 1 OH, just like above, it would be pentanol. But because we have 2 OHs, we'd call this pentane diol. Okay, so di meaning 2 alcohol groups. Where those OHs attached, they're attached to carbons 1 and to carbon 2. So 1, 2, pentane diol would be the name for this compound. All right, so now we're going to take a look at a couple of the organic reactions. And the first one here is looking at a hydration of an alkene. Okay, so when you hydrate something, you're going to be adding water, H2O. And for water in organic chemistry, you want to think of it as H connected to OH. Right, that's how you want to approach it, because the H is going to be added to one carbon, the OH is going to be added to the other carbon. And typically this reaction needs a catalyst, something to speed it up. And it's an acid catalyst, usually written with H+. So if you look at our example here, we have H2O, and then the H+ over the arrow means that is our acid catalyst. So when we hydrate an alkene, we're going to be adding H and OH specifically to the carbons that make up the double bond. Where does the H go? Where does the OH go? Well, the H goes to the carbon that already has the greater number of H's. And then the OH goes to the other carbon of the double bond. So that's all we need to do, is to look at our structure. So we have our initial alkene shown here. And this is a good example that shows you it's a fairly big molecule, but all the action really only happens in one location. All right, so we're going to add H2O and then our H+ catalyst. So we'll put the H2O in blue so we can see what happens. So there's our H and our OH, which is how you want to think of water. So where's everything going to happen? It's going to happen at the double bond specifically, and even more specifically, the carbons of the double bond. All right. So according to what we just said, if we're going to add water under this hydration reaction, one H goes to one carbon of the double bond, and the OH is going to go to the other carbon of the double bond. So the H is going to go to the carbon that already has the greater number of H's. So this H here is going to go to this carbon, because this carbon has 2 H's attached, which means the OH then is going to go to the other carbon that has a lower number of H's attached. And that's the only thing that's going to change in my structure. Everything else, this left side here, this right side, doesn't change. It's just where the double bond is that the changes are going to happen. So I can draw everything that doesn't change first, and then I can see how the molecule actually changes. Okay, so now This will highlight it here. Oops. So there's my C. And I have my highlighted region, and I have my other C over here. So I originally had a double bond between them, but when I add something to this carbon or either carbon, that double bond has to be converted to a single bond, because remember, carbon can only form 4 bonds. This carbon here already has 2 H's. We're adding another H to it. So guess what? It's going to have 3 H's now attached. And the OH then is going to go to this carbon here, which is this one. And I'm just going to add that OH like so. So now you'll see this carbon started off with 1, 2, 3, 4 bonds. And now it still has 1, 2, 3. But now the double bond goes away. We replace it with a new single bond to that hydroxyl group. So we've actually made now an alcohol, right? When you hydrate an alkene, you add HOH to it, you make an alcohol as your product. So your product here is going to look, when you draw it in ALEKS, it's going to look just like the original thing, with the exception of the double bond goes away. An H gets attached to this carbon, and then the OH gets attached to the other carbon of the double bond. All right, so now we're taking a look at some general types of reactions, so oxidation and reduction. And when it comes to oxidation and reduction, that's going to depend on the molecule that we're starting with. So here we're given a structure that looks like this. So we need to identify what family this belongs to and what we're doing with it. Okay, so the functional group present here is this thing, and this is an aldehyde. And this here tells us that we're going to be oxidizing it. It actually tells you so in the problem itself. So a couple of things to keep in mind: when you oxidize an aldehyde, what we should end up with is a corresponding carboxylic acid. Okay, and just like with the previous couple of examples, the only change that's going to happen to this molecule is going to be right here. The other part of it is going to stay the same. So we can draw the remaining section of the molecule. Then all we're going to do is to convert this aldehyde portion into a carboxylic acid. And the only difference there now is, instead of this H there, we're going to make it into an OH, right? And that is the only change that happens in this. It goes from an aldehyde into a carboxylic acid. So identifying what type of molecule you have to begin with is important, and identifying the type of reaction, which you're actually told in a couple different places here, what we're doing. All right, so the structure is going to look the same, with the exception of the region here on the right side. All right, so in this one, we're going to take a look at dehydrating alcohols. And this is an example, and we see this a lot in organic chemistry, where a reaction just looks like the opposite of one we've seen before. So dehydration kind of sounds like hydration. And if you remember, when you hydrate an alkene, right, you get an alcohol. Well, if you dehydrate an alcohol, you get back the original alkene. We're going to remove water in the form of HOH, which is the same way which we added water when we hydrated an alkene. And if you take away HOH, you're going to introduce now a carbon-carbon double bond. We're going to turn this molecule into an alkene. So if we have our structure that looks like this. All right, and then we have the correct conditions also. Remember, when you have your organic reactions, what kind of clue you into the types of reactions are the actual conditions that are present. So we have an acid catalyst, we have some heat, right? That's what the triangle means. And we have an alcohol to begin with. So we're going to lose H and we're going to lose OH, and together they're going to make water. So obviously we can see where the OH is lost here. We're going to lose an H from an adjacent carbon, right? So this carbon here in blue is where we're going to lose the OH from. And then we have a choice. We can lose an H from the carbon on the right side, which is our green carbon. We can lose an H from the carbon on the left side. And there are rules that that dictate which one is going to be preferred. But in our case here, we're looking at an alcohol that's symmetric, so it doesn't really affect us for our class. The point here is we're going to lose an H from either one of these carbons here, the orange one or the green one. So when we take away, all right, so we're losing an OH and H from adjacent carbons. And we're going to introduce now a carbon-carbon double bond. So obviously, if I take away this OH from the middle carbon right here, that carbon now needs, in order to satisfy the octet rule, it needs to have an additional bond because it already had an H to begin with that's not shown. So we need to show where that additional bond is. In this case, we can introduce a double bond there on the right, or because it's symmetrical, we could have put the double bond on the left side. Okay, and then we would have lost a hydrogen from either of these carbons here on the left or the right, so that they don't violate the octet rule in their situations as well. All right, so now we're going to take a look kind of similar to what we looked at previously, identifying reduction oxidation in organic reactions. And again, here now we're looking to see, we're comparing the reactants that we're starting with to the products that we end up with. All right, so you have a bunch of stuff here in the middle. Again, these are the reacting conditions that we have, any specific reagents that are needed for this. But what we want to focus on here is, well, again, the structures that we're starting with and the structures that we're ending with. So if I take a look at my molecules, all right, what I'll see is that in the original molecule here on the left, I have a C double bond O. I'll highlight this region connected to an H. And then we have our benzene ring here on the left side. On the product side, I also have a benzene ring, but now that C double bond O is gone, and it's replaced by an OH, a regular old hydroxyl group. Everything else is the same, right? So I'll highlight the parts of the molecule that doesn't change or that don't change. And that's the part in yellow. So all we need to do is to focus in on the blue and the green regions. That's the only portion that changes. We need to see whether this thing has become oxidized or whether it's become reduced. So one quick way that we can identify oxidation reduction in organic reactions is to see whether we've gained oxygens, lost oxygens, gained hydrogens, lost hydrogens, whether we've increased the number of carbon to oxygen bonds or decreased the number of carbon to oxygen bonds, right? So if I focus in here now, I can see that I'm just going to draw the region in blue, and then the region in green. I'm just putting in the H's there to show that carbon hasn't violated the octet rule. So obviously now we can see, if we compare what we were starting with to what we're ending with, right? We have one O to start with. We have one O to end with. I have one H here to start with, but now I have 3 H's. So we've actually gained H's, gained hydrogens, and gaining hydrogen is an example of reduction, right? That's a quick way to identify this. So in our example, we're showing here the reactant, and we need to highlight in red any groups that are oxidized, or in blue any carbons that are reduced. Obviously, now we can see that the carbon has gained a bunch of hydrogen, so it is being reduced. So you can highlight that carbon in blue, and we can check and see that that's correct. So when it comes to identifying oxidation reduction in organic reactions, I would say to quickly look and see whether things have gained oxygens, lost oxygens, whether they've gained H's or lost H's. Right, that'll tell you really quick whether we have one or the other occurring. All right, so here we're given now a reaction, and we're looking to see or to predict what the product is going to be. So we're given this structure, and we're told that it's reacting with hydrogen, with a PD, a palladium catalyst, and this would be the conditions necessary for reduction. And it's actually, you're actually told that that's the topic here that we're looking at. So again, with your organic reactions, you really want to look at what you're starting with. So this thing here, this family that this molecule belongs to is a ketone, because you have the carbonyl right here. That's between two carbons on either side. And when you reduce a ketone, these carbonyl groups are going to end up with hydroxyl groups. So all we need to do is to draw. We're not messing with the number of carbons. That's going to stay the same. So we're still going to have 1, 2, 3. All I need to do is to convert now that carbonyl into a hydroxyl group. So I change it to an OH because I'm adding a bunch of H's, as many H's as I need to my structure. The carbons don't change. And in this case, then I end up with the hydroxyl group. So that means it's an alcohol connected to a carbon, connected to other carbons. So I end up with a secondary alcohol when I reduce the ketone. If I had started with an aldehyde, for example, I would have ended up with an alcohol, but it would have been a primary alcohol. All right, so you'll see this throughout most of your reactions. And I mentioned this already. All the change is really going to happen where that functional group is located. The other parts of the molecule typically are not going to change.